we will move on to the consumable welding process, the third unit, right. Okay. So, in a GTAW, in a gas junction arc welding, it is non-consumable welding process where the electrode is intact, at least it does not melt. Okay. So, in a consumable welding process, the electrode melts and then the molten droplet is transferred to the base material, and then we form the weld bead by melting the workpiece or the base material plus mixing the droplet from the electrode, and the molten pool solidifies, we form the weld bead. Okay. So, in the consumable welding process, there are a lot of advantages compared to GTAW, because now we can weld much larger cross sections in a single go, because you add more material. Okay. The other disadvantage, main disadvantage we saw in GTAW is process efficiency, is not it, because the heat, if the electrode is electronegative, the heat is absorbed by cathode, it is lost. Whereas in this case, in consumable welding process, that is again transferred back to the weld pool, is not it. Suppose if you QA is in heat in the anode and QZ, that is a heat absorbed by the cathode. In GTAW, this is lost completely in electronegative conditions, is not it. So, only whatever heat is available in anode, it is what it is actually used, right. So, ultimately if you make conditions such a way that QA plus QC is transferred to the workpiece, that means that efficiency increases, is not it. So, in the consumable welding process, this is possible, because even if you have an electronegative situation and the electrode is absorbing the heat, or the generated heat at the cathode is transferred back to the workpiece, and of course, we also have a QA anode heat generated, and both are combined so that the efficiency of the process can be improved. Okay. So, that is also in a practical terminology, the GMAW is much more efficient than GTAW, because the both anode and cathode heats are transferred to the workpiece. Okay. So, we will see in physics. So, first we will see an overview video. So, we get used to the process, then we will go to the physics. How many of you have seen GMAW? So, what is GMAW first? Gas metal arc welding. Okay. So, what are the variants of a consumable welding process? Can you name some? Submerged arc welding, very good. And then these two? Flux core arc welding, very good. And then another famous, very commonly used, low cost process. Yeah, SMAW. What is SMAW? Yeah, shielded metal arc welding or manual metal arc welding or stick welding. Okay. So, these four are the most commonly used the consumable welding process: SMAW, SAW. What is SAW? Submerged arc welding, GMAW, gas metal arc welding, and then flux core arc welding. Okay. So, we are going to look at each processes, these four processes, but not just processes. I always say that we look at the physics of these processes. Okay. So, there are a lot of signs in these processes which control the stability as well as the arc stability, metal transfer, force balances, so that we can change the process characteristics, efficiency, heat input, arc energy, and so on and so forth. And we will also look at in the flux based processes, the role of fluxes. Okay, how are they going to affect the process stability and everything. So, since most of you have not seen the GMAW process, I will show you a video. Okay, so what we are actually doing it. So, what see over here is, so I see two electrodes. In this case, I use two electrodes to make this video, and we strike an arc between the electrode over here and the base material. So, the arc is struck. In this case, I am doing a pulsing. Okay. And during this process the electrode also melts by absorbing heat from the arc, and then the molten electrode droplets are transferred to the workpiece. Okay. So, and the nature of the droplet, how we transfer, that determines the bead geometry as well as the process characteristics. For example, so in this case it is like a spray, is not it? It is coming like an opening a tap spray, whereas here the droplets are transferred individual globules. Okay. And the characteristic of this transfer determines the stability of the pool. For example, in this case you may have a higher productive process melting, but if you increase the current even further, then you may also change the spray into some sort of a jet. So in this case a globular transfer can also be made into repelled globular by changing the current as well as the other forces, and you may end up creating a lot of spatter. For example, in this case you see the spatter formation, is not it? So when the globules got exploded once it enters the arc, say in some cases you see this spatter is flying away, is not it? See again. So these are all some the unstable conditions. So in this unit we are going to look at all the physical forces that are present during GMAW like we saw in GTAW, and we will also calculate how we can melt and what are the parameters that are controlling the melting characteristic of these electrodes, right. So again, so we look at all the physics behind the process. First, so the 4 important processes: gas metal arc welding, shielded metal arc welding, flux core arc welding, and submersion arc welding. So we will go in this sequence, because gas metal arc welding is the most widely used the welding process for engineering applications. Okay. And the shielded metal arc welding, it is also used for low end applications, but with large production needs. And flux core arc welding also it is widely used if you want to melt more and you will have to deposit more volumes per unit time. And submerged arc welding is widely used for welding thicker sections, because the efficiency is so high, so you can achieve a good amount of penetration, because arc is completely shielded. Okay, so the radiation and the convective heat transfer is minimized by completely shielding the arc. Okay, so we will see one by one. The first is the basic equation, heat input, and this is valid for any arc welding process. Okay, let us look at this equation in detail. The first question always arises, so what is the unit in the other side? Yes. So how do you define? So these equations. So what is unit of V? Volt. What is unit of current? I? Ampere. What is that ampere? So you will have to recall my first lecture. And what is V? Which is speed, isn't it? Right. So then what is in left hand side? LHS. What is that? What is unit of heat? Joule. Joules per meter. Good, because here we define is meter per second, right, SI unit. Okay. So LHS is joules per meter, and RHS is, there is no joule in RHS. Where does joule come from? VI. So how does VI becomes joule? Power. Power is joules per second. Again, where does joule come from then? From? From the work, exactly. So that comes from the basic definition of voltage and current. Okay, so electron volt EV. Okay, so the energy gained by the electrons while moving over a unit distance. So that is what the electrons gain the energy, joule. So that is the basic definition of voltage and the current, right? Isn't it? So I taught you in first class when you defined amperage. So 1 ampere is when one coulomb of electron travels in 1 meter. If they gain or if they spend 1 joule of energy, that is 1 volt, right? Or if they release 1 joule of energy when they are traveling from one point to other point, which is kept at 1 meter interval, so then it is 1 volt. So that is the basic definition of the voltage and current, 1 volt and current. Okay, that is the work done by the electrons while traveling over a potential difference, right, because they will have to work. So that is defined. So the joule comes from the work done by the electrons while traveling over a potential difference. So that is joules per second, and here we have meter per second, the second cancelled out, and then unit becomes joules per meter. So we always supply a heat input when you define joules per meter. And there is another guy here. So why we put this guy? Efficiency, I already mentioned here, isn't it? Yeah, so that determines how much amount of heat is transferred from the arc to the workpiece, isn't it? I just explained in the previous slide QA and QC. In a GTAW, if it is electronegative, QC is consumed, it is not transferred to the workpiece, isn't it? The whatever heat is consumed by cathode, it is gone. So that is why the efficiency is quite low, isn't it? So if in the cathode also transfers whatever heat is consumed to the workpiece, then efficiency increases, isn't it? So if you want to calculate the efficiency, we need to look at again the heat generation in the arc. So by looking at that, we can accurately calculate the efficiency, right? So we will do that because that is important. So without that, we cannot calculate how much heat you are actually inputting to the workpiece per unit length, right? So if you do not use an efficiency, and this is your arc energy, the energy is there in the arc, but all the energy is not transported to the workpiece. It is, some of them are lost because of the inefficient method we use to transfer the heat, right. So how do we calculate the efficiency? There must be some method, right, isn't it? It is just some number. So some people always say that 0.6, 0.7, 0.8, 60%, 70%. But as a welding engineers or welding scientists, we should give some physical background for this efficiency. Okay, let us calculate efficiency from the basics. Okay, like we did it in when you look at the energy transfer in the arc. It is very simple. So what we need to understand is again go back to the basics. So in the basics, what happens here? So we have an arc column and the cathode fault zone and anode fault zone. The voltages are not linear, isn't it? Except in the arc column, in the cathode fault zone and anode fault zone, you have a gradient in voltage. So this is the basic for heat generation we were talking about, right? Because of this gradient in voltage, we have accumulation of charges. Okay, so the accumulation transfers the heat, isn't it? In this case, if it is in the electrode is an anode, okay, the electrons are transported to the anode and that transfers the heat. Similarly, if it make it is in the electronegative, the electrons are transferred to the workpiece and that transfers the heat. by looking at this fundamental mechanism, we can calculate the efficiency. So, how do you calculate the efficiency then? So, we always know that we have 3 regions. Okay. The one region is the anode fault zone, and the other region is arc column, and then the third region is cathode fault zone. Suppose if we know the heat generated in each 3 regions, we can then using a simple heat transfer to calculate the efficiency. Okay. So, we can assume that, imagine now your the consumable electrode or the electrode is a cathode. Okay. At the cathode, what happens at the cathode? When we look at what is the main function of cathode? To emit electrons, isn't it? So, to emit electrons, it also absorbs heat, work function, isn't it? The work function, that means that it has to consume heat to emit electron, isn't it? And the moment the electrons are emitted and the electrons are sent to arc column, isn't it? So, when the electrons are at the cathode, the temperature of the electron is the cathode temperature, isn't it? The once the electrons are coming out of the cathode, then they also consume heat, otherwise the electrons will be in low temperature. So, once they go into arc column and they will have to attain the temperature of arc column, right. So, they also consume heat, isn't it? So, if you look at the amount of heat present in the cathode or cathode fault zone is the heat generated at the cathode, because cathode also has a current and the voltage, which is Vi, isn't it? That is the energy produced in the cathode, and then cathode also get energy from the arc, isn't it? The arc column also sends energy to cathode. The total energy in the arc is V arc column times the current I, but not all the heat in the arc column is not transferred to the cathode, right, only fraction, isn't it? So, we have the fraction of heat energy transferred from the arc column to the cathode, and these two are the energy gain in the cathode, isn't it? Energy produced at the cathode fault zone plus energy acquired from the arc column. These two are your credit, the energy credit, but this energy credit is spent by 2 ways. The one way is electron emission, which is negative term, right. And the second term is to heat the electron to the arc column temperature. When the electrons are there in the cathode, the electron temperature is the cathode temperature. The moment electrons comes out, then they also consume heat, because they will have to be heated up. Okay. So, the heat balance at the cathode fault zone is the heat energy generated in the cathode, energy acquired from the arc column, minus energy consumed to produce an electron, minus energy consumed to heat the electron which is produced to the arc column temperature, and that is the 3/2 K, the Boltzmann superstar. Okay. That is the electron temperature, and this is column temperature, so delta T. Okay. So, this is 3/2 K delta T divided by E. So, that is the equation to calculate the amount of energy needed to heat a particle to a temperature, right. So, we assume that, so electrons consume the heat in 2 ways, because the work function consume the heat, and then when the electrons are heated up, and then the electrons should be heated up to the arc column temperature, that is also consuming heat. Okay. These 4 terms make the energy balance at the cathode fault zone. Okay. And then now the energy balance in the anode fault zone would be plus terms, okay, because the electrons ultimately reach the anode, isn't it? So, now we have similar equation for the anode fall zone or the anode. That means that is a heat generated at the anode, and then the amount of heat transferred from the arc column to the anode, right, and then the gain from the electrons, isn't it? The electrons ultimately reach the anode. Whatever heat is consumed by the electrons will be gained in the anode, isn't it? So, your question is answered. So, whatever is consumed by the electrons would reach the anode, right, it is clear. So, you already see where the temperature will be high, where the temperature will be high in anode, isn't it? So, that is why when you keep electronegative, okay, so anode will be workpiece. So, the workpiece will always be in higher temperature than the cathode, isn't it, because of this balance. So, that is what when you are doing GTAW, if you are keeping electrode positive, the cathode temperature, your electrode temperature will be higher than the workpiece. So, that is not good for the stability of the electrode, isn't it, because according to this equation, when the electrons reach the anode, they also carry heat. So, whatever they gain in the cathode is transferred to the anode, is clear. So, that is why, so when you are welding, we always try to make sure that the workpiece is anode. So, that is the efficient process, so that we can attract the electrons bring the heat from the cathode and the arc column to the anode. Yes, it is clear. So, now the efficiency. So, efficiency is now based on the polarity, isn't it? How do you calculate? For the non-consumable electrode, when the electrode is positive. So, electrode positive means the workpiece is negative. That means that workpiece is cathode, isn't it? So, that means that from the anode nothing is coming. So, only the heat whatever is available is QC, isn't it? So, efficiency is nothing but the QC over VI. So, VI is the overall your I and then voltage. So, QC by VI times 100%, VI is the total energy available in the system over the QC times 100 is the efficiency, isn't it? It is not efficient process, isn't it? QC, cathode is always at lower temperature. So, if you make workpiece negative cathode, that is not efficient, because you are losing heat somewhere, electrons are not reaching, right. So, if you use the DC straight polarity or electronegative, your workpiece is QA. That means that the heat energy will be maximum, because all the positive terms, the electrons would also whatever the work function it gained, whatever temperature it gained in the arc column would be reaching the anode, the efficiency will be higher, right. It is clear, right. And then we can calculate QA and QC by using these terms. So, if you know the arc the cathode fall zone voltage, and the I is the actual E, okay. And then similarly the arc column voltage, work function we know K, what is the arc column temperature, electron temperature you know, and we can calculate now the efficiency very accurately, right. And for AC alternating current, it is an average, because you are changing the polarity every cycle. Yes, it is clear. And the consumable welding process, okay, in both DC and AC does not matter, because in this case whatever QC is generated is transferred back to the workpiece, either it is electronegative or positive. So, whatever if the consumable is an electronegative, you melt and again you are sending it back to the anode. So, the efficiency is QC plus QA together, is not it? It is clear, and VA is the overall, the energy. Okay, it is clear, and this is how we calculate the efficiency of the process when you are doing in a heat input calculations, right. It is clear. So, now according to these equations, which is the most efficient process? Consumable welding process, is not it, which is the least efficient process. So, when you have non-consumable with reverse polarity, where you make your the electrode positive, right, it is clear. So, in the both the cases this is not efficient GTAW, because in any one of the cases the electrode is not transferring heat, what is consumed, it is not efficient, is not it. So, that is why when you calculate the efficiency GTAW in the electrode positive case you have the least efficient efficiency. The maximum efficiency comes from a submerged arc welding process. Why? Because this factor becomes close to 1, is not it, because this factor gives the fraction of heat transferred from the arc column to the anode or cathode, is not it. So, this factor if it becomes 1, the entire heat generated in the arc column is transferred to the either anode or cathode, is not it. So, that term takes care of the heat transfer from the arc. Yes, it is clear. If this is close to 1, that means that whatever arc column heat is there, it is transferred to the anode and cathode. In submerged arc welding, the arc is closed. So, the fraction of heat transferred from the arc column to cathode anode is the maximum. So, this term the Ca and Cc becomes close to 1. So, the efficiency increases to very high amount. So, if it becomes close to 1, it will become 100% efficiency, because this is a consumable welding process. So, we need to add both QC and QA. In that, the fraction of heat transferred from the arc to the anode cathode also maximum. So, that is why it is very efficient process. Yes, it is clear. So, we can calculate the C terms by using a spectroscope, spectrometer, and we can identify the efficiency of the each processes. So, you see in plasma welding also, we also enhance the factor terms by constructing the arc. We maximize the heat transfer from the electrode to the workpiece, not the other direction, because plasma jet transfers the maximum heat to the workpiece. Yes, and the cylinder metal arc welding and GMAW will have equal the heat transfer. In the cylinder metal arc welding, it is slightly higher, because the fluxes also generate insulating vapor layer. So, that protect the arc from radiation. Okay, so, the efficiency increases because that factor term increases. Is clear? Any questions so far? So, it is a simple heat balance. How do you calculate the efficiency? So, it is not a simple like a term you use 50, 60. So, there is a physics behind it. So, when you are using a heat input equations. Yes, it is clear? Good. We will move on further. Okay, so quickly we will go, and then we will calculate in a consumable welding process using the same principle. We can also calculate melting rate, because that is already determined by the heat balance. So, melting rate of a consumable. So, how do you calculate? So, what is melting rate? The mass of electrode material melted and transferred from the electrode to the workpiece per unit time. We looked at the video, right? So, how do you make sure that you have the enough droplet transferred per unit time? So, you can play around voltage and current and then calculate, isn't it? But there is a fundamental way of calculating that from the heat balance that just I taught you in QC and QA, right. Let us do it and then we look at in detail the equations. So, melting rate we define as the mass of electrode material melted and transferred from the electrode to the workpiece per unit time. If you want to calculate the melting rate of wire, you need these two parameters. First parameter is latent heat of melting of the wire. Second term is the energy required to increase the temperature of the wire, the droplet which is already formed, to the droplet temperature, the wire temperature to the droplet temperature, isn't it? So, heat is needed to raise the temperature from the wire temperature to the droplet temperature. So, these two would be consumed, isn't it? So, what is available? Which heat is available? Latent heat is available. Okay, so latent heat and these are all consumed. Where is the energy supply coming from? Where does heat come from? Arc, right? Okay, so that is either QC or QA, isn't it? Isn't it? That takes care of cathode heating. Okay, the amount of heat is coming from the arc to the cathode, right, and then work function and then temperature consumed by the electrons. So, that is the heat is available either QC or QA, and additional another heat is also generated in this case if it is wire. So, that is Joule heating, isn't it? So, now the melting rate is nothing but these positive terms QC plus Joule heating, right, minus latent heat of melting. Okay, so, that you can say H minus and then the energy required to heat the molten metal to the droplet temperature. So, which is nothing but dt minus Tm times Cp, right. If you know these, we can calculate the melting rate, right. And what is QI? QA is, how do you calculate Joule heating? Is it I squared R, exactly. What is R? Okay, how do you calculate resistance? Rho L by, isn't it? Right, it's clear. So, we have now equations for QC and QA, we have equations for QI, we know H, we know this if you know specific heat capacity. If you know all these four, we can calculate the melting rate, isn't it? Yes. So, simple. QA is, suppose assume your consumable is an anode. What is QA? So, we can take I out because I is common, right, the current, isn't it? So, it becomes now the voltage in anode, the amount of heat transferred from the arc column to the anode, and then this guy, the work function, energy gained by the work function with the electrons, and then the energy gained by the electrons by the heating up from the cathode temperature to the arc column temperature, and that is I, and this is Joule heating. And these terms added minus latent heat of melting minus your Cp, specific heat term, that will give us the melting rate, isn't it? So, melting rate we can get the relationship now, and M. So, if you add all these four and balance the equation, So, you will get the I term comes from the QC and QA, and then the other term we get, that is from the Joule heating. So, L I square by pi r square, and A and B is now it is a constant. So, for example, this entire term is fixed for a given process. Suppose if you fix your electrode polarity, you make the electrode in anode, right, given a shielding gas, the efficiency is determined already, okay, for a given process condition, and this is fixed. It is clear? Yes or no? Because I is, we already taken out I, because I is a variable, is not it, and this is material constant, material specific constant, this is again material specific constant. So, now if you look at these equations, what is the important variables is current, and then L, and then R, remaining else is constant for a given process and a given material composition, is not it. So, the melting rate of a consumable is determined by the welding current. If you change the welding current, melting rate changes, and the other two important parameters, the R, which is the electrode diameter. If you increase the electrode diameter, melting rate decreases. The other parameter is L. What is L here? Length of the wire. In welding case, we call that length as a stick out length. So, what is stick out length? Suppose if you have an your CTWD or the electrode, the length of the wire which is sticking out from the contact tip. So, this is known as contact tip, okay, and then you form a arc here, and this is the workpiece, and this length L is known as stick out length. So, if you increase the stick out length, what will happen? Melting rate increases. So, for a given process condition, so if you fix a shielding gas, okay, then you fix this, is not it? If you fix a shielding gas, the heat generated in the arc column is fixed, right, and if you fix the material composition, then H is fixed, Cp is fixed, this term is fixed, right, and if you fix the electrode composition, the work function is also fixed, is not it. So, for a material given material composition and given shielding gas, and A and B are fixed. So, then the variables which can be controlled to change the melting rates are welding current, stick out length, and then the consumable diameter, okay. And if you fix the diameter also, that means that this also goes away. So, there are only two parameters can be changed independently, they are stick out length and then welding current. Yes, it is clear. So, if you fix all other things, shielding gas is fixed, therefore, the arc column heat is fixed, material composition is fixed, therefore, H is fixed, Cp is fixed, is not it. And then now you fix also fix the welding electrode diameter. So, R is fixed. So, what are the two parameters can be changed to change the melting rate? The welding current, stick out length, right. And in practical cases, we play around these two parameters to get good sound well bead characteristics. We change the stick out length and welding current for a given electrode, diameter compositions. So, when you buy an electrode diameter, see you plan to weld a 3 mm thick and say SX90 steel, and you have a equal similar filler, and you are establishing the process parameter. Okay. And then you need to now calculate the melting rate. So, your composition is fixed, you are buying a 1.2 mm diameter welding wire, your diameter is fixed, and you are going to use argon as a shielding gas. So, all other parameters are fixed. Suppose if you want to establish the welding procedure, two things you can vary is current and then stick out length. Yes, it's clear? It's good. So, with this we will finish this class.